1.3. Before we understand the theorem, let us understand this. So let us look at all the factors of 6 and its square 36. So factors of 6 are 1, 2, 3 and 6, and factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, 36. Suppose it is said that P is a factor of 36. So what can P be? Looking at the factors of 36 here, we can say that P could be any of these numbers. So it could be any of these numbers. It could be 1, it could be 2, 3, 4, 6, 9, 12, 18, or 36 itself. Now, can we say that if P is a factor of 36, it is a factor of 6 also? No, because 4, 9, 12, 18 and 36 are not factors of 6. You can see it here. 4, 9, 12, 18 and 36 are not factors of 6. So if we consider all the factors of 6 and 36, they are not same. Can we say that if a number is a prime factor of 36, it is also a prime factor of 6? Now we are limiting our factors to only prime numbers. And then prime numbers, if we look at prime numbers only, then they are same in both. So then our answer is yes, because prime factors of 36 are 2 and 3, which are also the prime factors of 6. Now, suppose it is said that P is a factor of 36 and P is a prime number. So what can P be? We know that it can be either 2 or 3 because we have seen that 2 and 3 are the only prime factors of 36. Let's verify using prime factorization. So if I prime factorize 36, I get 2 into 2 into 3 into 3. Okay, that is 2 square into 3 square, that is 4 into 9. Now, does that mean that 4 and 9 are the prime factors of 36? Or does that mean that 2 square into 3 square are prime factors of 36? Are 2 square and 3 square prime factors of 36? No. Square numbers cannot be prime. 4 and 9 are not prime numbers. When we talk about prime factors, we will only consider 2 and 3. Are 2 and 3 prime factors of 36? Yes, they are. And 2 and 3 are also prime factors of 6. Let us see the prime factorization of 6 and verify it. Yes, 2 and 3 are prime factors of 6 also. Yes. Can 2 and 3, both these prime factors, divide 36 and 6? Both? Can 2 divide 36? Yes. Can 2 divide 6? Yes. Can 3 divide 36? Yes. And can 3 divide 6? Yes, it can. So now we understand Theorem 1.3, which says let P be a prime number. Okay, it is given that P is a prime number. If P divides A square, then we need to prove that P divides A also, where A is a positive integer. Now let's also recall that A is a square root of A square. If we want to find square root of A square, we will get A. But remember, square roots can be negative also, but here we will only consider the positive square root of A square. Therefore, there is this mention that A is a positive integer. That means we are considering only the positive square root of A square. So, it is given that P is a prime number, and it is also given that P divides A square. We need to prove that P divides A also. Okay, so let's see the proof. Let the prime factorization of A be as follows. So let A be P1 into P2 into P3 into as many prime numbers that are there. So we will keep it till Pn, okay? So let all the prime numbers of the product of all the prime numbers be written like this. So P1 into P2 into till Pn, where P1, P2 and till Pn, all these variables that we are taken are prime numbers, not necessarily distinct. That means they could be repeating also. For example, if we are taking a number 4, then 4 can be written as 2 into 2. So you can see that 2 is repeating itself. But if I'm taking the number 15, then 3 and 5 are distinct. But here they are said not necessarily distinct. So it could be a number like this, 4, or it could be a number like this, which is 50. Both the cases are considered here, okay? Now, therefore, the prime factorization of the square of A, that means A square, will be whatever the prime numbers are there in this here they are going to appear twice and they are going to multiply, so we will get square of all of them. For example, P1 into P1 will get us P1 square, P2 into P2 will give us P2 square, and as many, all the prime numbers will become the squares here in the prime factorization of A square. Now, for example, 16 is a square of 4, and you can see if there are two 2's here we will get 4 2's, okay? Because for each 1 2 there we will have double 2's here. So for another single 2 here, we will have double 2 into 2 here. So we have 2 square into 2 square, which is 4 into 4, right? And here also, if you consider the square of 225, you can see 3 is here in square and 5 also is here in square. So if a number appears once here, it will appear 2 times here, and so it will turn and it will multiply, so it will become a square. So we have 3 square and 5 square, which is 9 into 25. But when we consider the prime factors, remember the prime factors of 225 are only going to be 3 and 5, not 9 and 25, not the square numbers. The prime factors of 16 are only going to be 2, only one prime factor 2, not 4. 4 is not a prime number, okay? So similarly, prime factor of A square are not going to be P1 square, P2 square. Prime factors of A square are this, P1, P2, and all of this, okay? We are given that P divides A square. It's given here that P divides A square. Now remember, P is a number we have taken in this question, which is a prime number. So if P divides A square, then P is a prime factor of A square. According to the fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square, right? But the prime factors of A square are these, P1, P2 till Pn. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that here the prime factors of A square are P1, P2, Pn, because that's what we have taken as A, and A square being a square of A will also have the same prime factors. So according to the variables that we have taken, prime factors of A square are P1, P2 till Pn. So that means this P has to be one of these variables. So P will be either P1, P2, or Pn. So P is one of these numbers here. P is one of these numbers because they have to be same. And so if P is one of this, then P1, P2, and P3 and Pn till Pn are also prime factors of A. You can see it here. They are also prime factors of A. That means P is also prime factor of A. and therefore P divides A.